Hello, everyone, and welcome to today's SANS webcast, Preventing Runtime Exploits, the SANS Implementation Guide for RunSafe Security's Alkemist, sponsored by RunSafe. My name is Jessica Gallus of SANS, and I'll be moderating today's webcast. Today's featured speakers are Shane Fry, Director of Security Engineering at RunSafe Security, and Christopher Crowley, Senior Instructor at SANS and Consultant at Montents. If during the webcast you have any questions for our presenters, please enter them into the Q&A window located on the control panel at any time. Please note that this webcast is being recorded, and a copy of the slides and recording of this webcast will be made available for viewing and can be found on the SANS webcast archives. And with that, I'd like to turn the webcast over to Shane.
Thanks, Jessica. Let's see if I can. As Jessica mentioned, I'm our VP of Security Engineering at RunSafe Security, and I'll be giving a brief overview of the product that Chris and team at SANS did an analysis on. Quick note on the agenda, I'll go through the RunSafe tool, our company, and the Alkemist tool product, and then give a description of our technology and its intended use cases before we hand it over to Chris to discuss the assessment that was done and provide some examples and details about the assessment. So, a quick overview of our company. RunSafe Security's mission is to disrupt hacker economics by immunizing software from cyber attacks. And what we mean by that is we're not trying to stop every single possible security problem in the world. I don't want to sell snake oil. But instead, we want to be able to be really focused on memory corruption attacks, and we're going to disrupt those hacker economics by changing the code and the memory layout that attackers need to carry out attacks successfully. So, what does our Alkemist product do? It enables you to have continuous security across build and deploy tool chains. This slide's a little bit more DevSecOps focused, but it applies to however you're getting and building your software. We have two modules to our Alkemist product, Alkemist Source, which can be laid in at build time, and Alkemist Binary, which can be deployed against binaries that you may not have source for, or you may have source for, and you just want to make changes to those at the binary time and post-compilation. So before we get into more of the technology details, let's talk about the problem that we're trying to solve. So this data here came from a NC State report that is not yet published, but we got a pre-published copy of the data. And they went through for a variety of open source projects, the Linux kernel, Firefox, Samba, LibreOffice, etc., and did some analysis of the alerts that static analysis tools had found for those projects. And you can see in the table on the right that somewhere between 28% and 46% of the alerts that were found were memory related. And so the average there is about 35% of the alerts that were found are memory related problems. And so Alkemist is designed purely to solve the memory corruption problem space. So how it works is we have unprotected software, whether that's in source code or binary form. It goes through our Alkemist transform engine and produces protected software on the outside. Now, unlike some software out there, we're not an agent that installs on your system. We're not instrumenting your binaries to find control flow deviations. Those are really expensive from a computation perspective, from a performance overhead perspective. And most of the time, they only work if you catch the attack after the attack has been successful. So we want to protect kind of the last mile of computers and software before they get attacked. So we've got kind of three different transform techniques in our Alkemist product. On the left side, you'll see a standard Hello World program that's been compiled. There's a header, whether it's L for PE header, you have your header there. And in your text section, you've got functions 1, 2, 3, all the way to function in. And each of those functions contains a set of basic blocks that make up the functionality of that function. So that's the normal Hello World program. We've got our load time function randomization. This is what Chris is assessing and presenting the results of that assessment. So we'll dig into a little bit more detail about this one. Basically, we go in at load time when any program is loaded, when any shared library is loaded, we go and we randomize the order of the functions in memory. So attackers that are using return to libc or ROP style attacks won't be able to know where any code is in memory. And this is completely complementary to ASOR, and in fact makes the ASOR approach even more effective, because a single memory leak in a module protected with ASOR doesn't completely defeat the randomization in place. On the binary side of things, we have two transforms: basic block randomization, stack frame randomization. Basic block randomization goes in, and for each function, we keep the functions in the same order, but we shuffle the order of the basic blocks there. Again, we're trying to disrupt those ROP and JOP style attacks. And then we have stack frame randomization, where for every function that has a local stack frame, we add a random offset in there so an attacker can't know how many bytes to write when they're trying to exploit a buffer overflow. So with our load time function randomization, I mentioned we do this at function load time. So normally in a Hello World program, or even in Python or browser, you have an entry point that's specified in the header that executes, that points to your original entry point. When we lay in our protections at build time, which by the way, when those come in at build time, you can use your standard GCC, LLVM compilers, linkers. We just sit in front of them to gather some information we need, make some changes, and then let the build proceed as normal. So when we add in our stuff, you see an extra library dependency, liblfr, and we get a new entry point in the program. It's the only code we add to the actual text section of the binary, and that code only exists to call into the liblfr function, library rather. We randomize all the functions in memory, and then we pass that entry back into the original entry point, and execution continues as normal. So what you see here is a really low cost from a performance overhead perspective to the boot time of a process, but no runtime modification to your performance, because once you're in the original execution of program memory, the only thing that really is going to change is whether or not you're getting cache hits or misses. And so pretty much everybody we talk to isn't even measuring cache hits or misses. So we can allow you to kind of meet whatever real-time requirements you've got and still get protection against memory corruption attacks. So in general, what are the use cases for the Alkemist product? You can apply it to, if you're a critical infrastructure manufacturer, or if you're deploying critical infrastructure, you can protect the software that's running on your systems. It applies to enterprise IT software, mobile devices, etc. Now, I'll caveat that by saying we only protect compiled code, so we can't take in a Java application on Android, but we can protect the shared libraries that are running on an Android system, for example. In manufacturing, again, more of the IoT type space, we can apply our techniques there. It applies to military systems as well as software companies that are just producing software. So if you're the developer of Zoom, for example, we could apply our protections to that. But pretty much, if you're building software, if you're running software, either Alkemist source or Alkemist binary is applicable to you. And before I hand it over to Chris, just want to note you can get more information, both from a marketing perspective or from a technical perspective, on alkemist.runsafesecurity.com. And if you scan that QR code, that's going to take you to the website as well. We do offer a 30-day free trial, no credit card or anything like that. So you can literally just go and use it, see how it's used, and test the effectiveness of it as well. Now I'm going to hand it over to Chris.
Great, thank you very much. Appreciate the introduction and the overview of the product. Basically, this webcast is discussing a paper that I'm writing. It should be out here shortly. Basically, there's more technical detail in the paper. What I was asked to do is take the product, assess it. The RunSafe was looking for basically a third-party assessment in place. The paper has a lot of details on the methodology. And of course, this is one of many scenarios that are of interest. And so we focused in this case on a basically circumstance of a web server in order to basically protect this. But that the whole thing was open when we started off, and basically RunSafe said, hey, we'd like you to look at our product, see what it is. We should be, protecting against a bunch of different exploits. And so there was some sort of initial back and forth in terms of what exploit would actually be selected. There were a bunch of different things that were characteristics for the exploit in order to make the selection appropriate. It had to be something recent. It had to be something, from an exploit perspective, it had to be something recent. There had to be proof of concept code that worked effectively against a system that I could actually build the code and then build the protections into it. It needed to be something that wasn't so esoteric that nobody would care about it. And so this was the point of the assessment. This is what I was asked to do. Several people double checked my work, and I do appreciate those of you who spent time taking a look at this. This was a fairly involved and complicated assessment. So the methodology was basically RunSafe provided me with a license, and then I started testing against a bunch of different sort of applications. It started off with very simple stuff. They have a sample hello world sort of application, took a modified version of that, looked at it a little bit further, then started to look for the more interesting proof of concept or exploits that were released. And I tried to compile from source in order to make sure that I had a very sort of directed comparison. But at the end, when I talk about this, the libc that I ended up installing was actually something that that RunSafe compiled and provided to me. The idea behind that is you don't have to compile it, but my intention for directly compiling from source was to have two things. One was to make sure that I had the correct version of the thing that I was trying to exploit, and then two, to make sure I had an exact comparison. So there wasn't some change in the in the compiler flags that ended up causing something that was different. So that was why I did a lot of Apache compilation from source in order to look at this initially. Now, why you should care about this? Well, a lot of organizations are running web servers, and there is quite a bit of interpreted code sitting on top of this. And this was an area of interest, when we first sort of talked about what things were on the table in terms of exploitation. This was an area of interest, is the compiled code going into the native space in an attempt to protect that. So looking for all these different attributes, I ended up finding a proof of concept exploit, which had a valid CVE, which actually worked. And this is called CARPE DIEM. And so I'm going to be talking for most of the rest of the presentation about this particular exploit, and then the sort of assessment that I did around this particular one. Now, Apache child processes or worker processes run unprivileged. They run unprivileged because they're serving pages out to an internet request. But as it turns out, there's actually a parent root process which is running, which is responsible for starting Apache up, managing those child worker processes, doing the logging, and so on. And so the CARPE part of this named exploit is CVE Apache root privilege escalation. And so this particular attack actually provides root level privilege escalation from a non-privileged state. And so this security strategy is sound, except for the fact that the child processes and the parent process actually share an area of memory. And so this is ultimately what is going to be attacked. And I'm going to be talking about this, and there again, I'm going to provide a lot of details. So I want to be very clear. I'm going to repeat this multiple times. In the write-up and the information that was provided that I implemented and then used, there are actually two different flaws which Charles Foale identified. One was a PHP use after free. I'll talk about the use after free and how that works. The other one was what is called this CARPE DIEM and has the name CVE. And this is essentially an Apache out of bounds read where the root process takes data from a child process, which has been modified and ends up sending direction to the parent process, which causes the parent process to perform an operation that it shouldn't perform. Okay, so when I talk next about the technical details, I'm going to, the titles of the slides say this. I'm going to be talking about this, but at a certain point, I need to start to bounce between these two different flaws. So try to keep them straight, and I will try to keep them straight in my explanation. When this was released, the PHP use after free portion was actually 0 day. Charles Foale, said that when he released this, he had previously contacted the PHP maintainers, but they hadn't addressed the problem and they hadn't responded to him in a timely fashion. So when he released the CVE 2019-0211 write-up, the PHP use after free content was also released, which was 0 day at the time. So basically in the assessment, I was working through this, tried a couple of different candidate packages in order and proof of concept exploits, found this one, got it working effectively, recompiled the Apache with the libLFR protection, which is basically, I just compiled it in terms of its normal compilation to match the environment that Charles Foale used in order to attack when he developed this. And then I took the helper script that comes with Alkemist, compiled the Apache again, launched the exploit, and it still succeeded. And I was sort of like, I don't think that's what they were going for. And so I talked to RunSafe. I sort of dug down into it in terms of how it was working. They looked at it further and realized that the Apache component was not actually being protected. So the out-of-bound read portion is not stopped by the function randomization at runtime, because it actually doesn't depend on a function being in some specific place. It's the program operating as it was coded. And so even after the fix got put in, which I'm going to talk about the fix in a few slides, even after the fix got put in, the vulnerability still existed in the Apache. Even with the Apache compiled with libLFR function randomizations. But this is specific to this instance of this particular out of bounds read. If there were some other different flaw which did depend on a randomized location, a memory and location that was randomized, this might protect it. So,
and Chris,
hold on the component of the assessment at the moment, and I'm going to come back to the idea here of the protections that were actually put in place. So let me talk about how the PHP code worked in order to leverage the use after free exploit. So before I get there, I want to also just sort of mention, like, what might this look like in the wild of where an attacker would be in a position to be able to leverage this particular attack. So I basically am thinking about two primary scenarios of where this might happen. The first one is some sort of a hosting environment, a managed service provider, some sort of departmental web server, basically where the clients are authorized. They're already given credentials to get onto the system, and there's a PHP web server that is in place. And that client decides that they want to go after root, And so they upload the attack page, and I'll show you the attack page. They upload the attack page and then use it to perform some action that grants them root in a, probably a secretive way. The other is similar, but it would necessitate some other external exploitation via probably a web application. Could be some sort of a local file include that allows for the attacker to be able to upload a PHP page, which they then subsequently request. Any of the various web application type attacks that would allow them to upload a PHP page, SQL injection that allows you to dump some stuff, that you write out an arbitrary PHP file, including this exploit code, and then call to the PHP. Okay, so this is sort of the setup of the attack of real world scenarios of where this might happen. And so in reading through this write-up, his details were really quite excellent. Lots of technical and low-level sort of explanation of how the exploit is working, which is not the case with all proof of concept code that's out there where people are talking about it. There's a lot of hand waving sometimes. And so this was sort of a refreshing explanation of how it worked, very well documented, very clear in its articulation of what the actions are. So I'm going to talk about the use after free because it's relevant to the protection that is ultimately in place. But I also want to sort of provide the details of the boundaries of what you can expect from the LFR to actually stop so that there's sort of a clear understanding of that. So the use after free flaw is present in an older version of PHP, which has subsequently been patched. This was came out at the end of 19. And the way that this worked was a class, in this case, we're calling it class X, extends a class which is data interval and implements the JSON serializable capability. Then the serialize sort of function is called, in which case there are actually two variables defined, y and p. Y is instantiated, but then unset. And then P is defined as a handle to what was a Y using this. So this Y now actually allows modification of the contents of the memory space that was allocated for Y by using P. And so this use after free now allows for writing into memory and reading from memory. And so this flaw, like I said, has been fixed, but this flaw is then used in this attack in order to structure the heap in such a way that the attack against Apache will have poisoned content in memory so that when the Apache server restarts, it gets tricked into eventually running a system call. Now, I'll mention this again later, but there are two ways to start Apache. Apache CTL restart that closes the parent process, starts a new parent process, and away things go. There's also Apache CTL graceful. And what Apache CTL graceful does is it actually tells all the child worker processes to exit and then respawns new child worker processes. And in so doing, it checks the state of the memory of the child worker processes which exited and actually looks for the code that's in shared memory for those child worker processes in order to see if there's anything that needs to be continued by the new child worker processes, which are started as part of the graceful restart. Okay, so the other thing that's really important to think about for this is that it actually provides memory that continues from one process to another because the parent process does not exit. And so this exploit, which I'll talk about how it does this, but this exploit uses a PHP Zend object, and it is going to take the destructor method of that Zend object and map it to the system call that is available to the Apache process, so that when it wants to do something, ultimately at the end, it's going to use that memory mapping to the address of the system call. Okay. So the use after free is in place where the Zend object, which is $P, is actually changed to a Zend string. This has the benefit of now being able to change the length of the object to be able to write into arbitrary places in the heap by extending or shortening the length of the object and then writing to it. It can write further and further and further into memory. The intention of this writing into memory is that the child init method of the children, which were running but end up being sent a signal to stop, the child init method will actually be rewritten to call the address of the Zend object standard destructor in order to be able to then rewrite, to map that to the location of memory where the system call is. And so it's kind of nice, this exploit proof of concept is very well written, and it's so nice that it actually gives you the opportunity to provide a parameter of the specific command that you'd like to execute when the server gracefully restarts. So this takes it as a parameter. The PHP exploit, in order to be able to craft the memory correctly for this, is going to basically read through the memory using the freed object, and is going to basically find the bucket address of each of the child processes. Now, the bucket address refers to an Apache web server memory structure. This gets very complicated in terms of the memory objects which are in place. I talk about it a little bit more in the paper. I'm going to try to provide a clear summary of what's happening here, but it is, again, the sequencing of this is fairly complicated in terms of how the memory in the shared memory area needs to be restructured. So what the use after free exploitation is going to do is going to find a whole bunch of buckets in the locations in the shared memory, and then it's going to create a whole bunch of lookalike child buckets in order to make it so that the exploit will probably work when the server gracefully restarts. It is going to create a payload. The payload is constructed via several parts that it needs to assemble in order to be able to write the correct memory structures for this to execute successfully. This will then spew all these different child worker buckets into the heap, but it's actually going to leave one specific bucket open right at the very beginning in order to be able to write the payload value. The payload value is the combination of several parts. It's the method, the properties, and the child init that's actually going to be in place, and the memory address of the payload of the command to execute. So first, it checks to be able to determine if this bucket value is set. It's going to assign that to the bucket value. The payload is going to be the bucket address, the method for child init. The child init method, however, has been mapped and is going to be mapped by this. Instead of being the actual child init method, it's going to be mapped to this Zend object string destructor. This is going to be followed in memory by the properties attribute. In order to execute the system call, this is going to be the memory address of the system, which is the properties attribute, in terms of what is being built for the child lookalike bucket. So the payload looks like a child bucket. It's structured in the right way for this child bucket to be absorbed, inspected for data, the addresses are extracted, and then the new child is going to be forked, and these data attributes out of memory are going to be used to create the new child process. And it's important that these portions of the execution occur prior to the fork of the child process. And I'll get to that in a moment. So the area for the heap spray is determined again by looking through the heap. After we have this initial component, all of the different child worker processes are enumerated. The process IDs are available in the shared memory. This information is used in order to be able to basically replicate this structure throughout the heap in order to increase the opportunity for success. And once I got this working properly and started to understand the mechanism of it, it worked basically every time that I triggered the exploit. I had some, it was a very complicated build out because I needed to get it exactly right. For the way that it existed when he developed the exploit, which was basically an Apache instance from a year and a half previous that was compiled by the package maintainers. So I had to go find the right build options for it. But once I had that and the correct version of PHP, which also was an older version, which wasn't easy to find. But once I ultimately found a repository that allowed me to have that, then I was able to, to structure this. And when I ran it on a vulnerable instance, it succeeded almost every time. I would say, 90% success rate. 1 out of 10 times, maybe it wouldn't work. And then I'd re-request the PHP page and it would succeed. So when it was vulnerable, this exploit was very reliable. And I have a couple of videos and I'm gonna demo this for you, but let me get through the explanation of it before I go into the demo. So just to reiterate, I'm talking specifically about the graceful restart state. Apache CTL graceful, actually the parent doesn't exit. So the memory structure that's in place largely stays the same. There's certain things that are done in the PHP portion of the exploit to make sure that the restart survives because of the way that the child workers are stopped and so on. Those details, if you really need to know all of those exact details, you can either read Foles write-up or you can read some of the stuff that I include in the paper. But basically, the memory survives enough in order to be able to be picked up by the parent process when the parent gracefully restarts. And so this is a little bit of an example of the circumstance where this exploit was ultimately successful. The mutex reported from the CARPE DIEM PHP exploit page output matches the mutex from the GDB output, where I'm actually watching the Apache server as it's doing the graceful restart in order to enumerate the memory components. And there were multiple different child workers which would be handled. And the code, the vulnerable code, is actually the prefork.c code. And I'm going to talk about the Apache flaw momentarily. This graphic is intended to show you that, yes, the exploit is finding the mutex. The mutex is correct. The places to write in memory are all correct. And this is all shared memory as part of what the PHP, again, interpreted code running inside of the Apache process, part of what it is actually able to see. So now I'm starting to move into the Apache out-of-bound read portion of this. The Apache starts as a root process. The root process has some shared memory where the child worker threads, which are running in this particular instance, UID 33 named www-data because that is the exact compilation method for when he was actually developing the proof of concept exploit. So there are several memory structures that are involved in this. There's the scoreboard, which is used to track the child processes. Each of the different workers have their own bucket, but then they also have a mutex in order to manage communication inside of there. So graceful gets called. The parent starts to look through the shared memory for the portions of each child in order to make sure that their code is preserved, because the point of the graceful restart is to provide continuity. It can stop the child workers, but then start up new workers very quickly in order to basically have those child workers that were in place prior to the graceful request. They can just finish off their action and be done, but then it's going to, the parent is going to say, okay, now I need to restart child processes. And there are a couple of reasons why this happens. This is either there was some modification to the configuration of the Apache server, and you want to basically reread the configuration file. Most commonly, this is done for rotation of the Apache web server log. Hence the second part of the named exploit with CARPE DIEM is that this happens on almost all web servers once a day. So there's daily opportunity for exploitation. Once the malicious child poisons the memory that's available, it just needs to wait for the parent to come along and stop all of the children, and then go ahead and do its thing in order to fork new children, at which point the memory structure is going to have been tainted and poisoned, and then it will be reread. So the tracking happens via the buckets and the scoreboards in terms of what the child is doing. The flaw in the Apache part of the code is that the modification of the memory is neither detected nor prohibited by the parent process, and so the malicious child process modifying the memory is able to provide instructions which shouldn't be allowed to run. And so the highlighting that I have on here is a comment that's in the Apache code. And so the link at the bottom of the slide is highlighting line 431 in the prefork.c in the server npm code. And so this is performed prior to dropping root privilege in order to make sure that the environment allows for the actions which need to be done. Okay, so the parent is trusting the shared memory to be unaffected and is going to read through it. And basically, the mutex for the child in it is going to basically, each child is going to have their own bucket pointing to their mutex. And this is what is going to be called with the safe accept. Of course, has a couple of conditions in order to make sure that it's not vulnerable. But in this case, the conditions are met, and the modified bucket represents the attack. So by the heap spray, the child init method is pointed to the Zend object destructor method of the P object. And P's P destructor method points to the memory address of system. The AR data of P points to the address where the PHP attack code stored the command to run. Okay, so this is all crafted in the PHP use after free in order to set up the bucket, so that when the Apache process reads this, it's like, okay, this is, the data structure is correct. Now, things have been pointed into the wrong place. If things have been pointed in memory into the wrong place. The Zend-object string destructor method isn't really appropriate for the, for the child init, but that's where the tainted buckets are pointing to. And so this destructor method is pointing to system, which is available inside of the Apache process. And the PHP attack code, the command that I added as a parameter, is also in memory, waiting to be called by system when that destructor method is called. Okay, so I'm going to switch to the video here. Make sure I have the right one. And I'm going to just sort of walk through what the video is talking about or trying to show to you. So in the paper and in a couple of slides, I'm going to highlight this, that there are slightly different name structures in the unprotected versus the protected libc system that's in place. You have some GDB output on the screen here. You can see that at a specific memory location, the cp/etc/shadow/root/seized. Now, I could have copied it anywhere, but that was just convenient for me. This is GDB that I was running on the on the Apache server during the graceful restart in order to be able to watch the action. GDB is not actually still running in this video. I stopped it in order to just demonstrate the exploit, but this was basically what I was working through. I've got a little a little script that I run in this bottom window in order to basically show you that this is looping until the file named seized it does not exist. It is looping while the file does not exist, and as soon as it does exist, it will exit. So it's looking for and just basically spitting out the date, is looking for the file, and as soon as it sees that the file is present, it's going to exit this loop, and then it's going to do a long listing on that file. Okay. So the next thing here is the request that's made. The attack code of the PHP attack code here is that cp/etc shadows/root/seized on the parameter line of the URL that's being requested. This will run and it will show that the exploit is successful. This is specifically the PHP use after free exploit that it's referring to here. It finds the various PIDs. There's a whole bunch of output that's spit out by this PHP script. It tells exactly what it's doing, where it's writing things in memory. Really quite effective in terms of understanding what it's doing. It was still fairly involved in terms of doing the Apache inspection of this, but this output was incredibly helpful. Now, I'm going to basically do the work for the restart. Here again, just a script, because I was doing this repeatedly over and over again. I removed the file because, as I said, once I got this working, this worked great. I removed the file. I gracefully restart Apache. I wait a couple of seconds, and then I do a SHA-1 comparison of etc shadow and root seized it in this sequence of commands in order to basically prove that it worked. And I had done this multiple times and basically over and over and over again. It just keeps working, right? And so as soon as I run this, you'll see in the bottom right-hand corner that the seized it file is present. There's the seized it file. I get a long listing. 3 seconds later, I get the root seized it in the directory that is basically the successful exploit. That, as I mentioned earlier, was successful against Apache, and then it was successful when I compiled Apache with the liblfr protections. Why? Because the randomization that is provided when I recompiled Apache is actually randomizing the structure of the functions at runtime in Apache's memory, in Apache's executable code is really how I should say that. And so that randomization doesn't break this exploit because the exploit is not dependent on the executable methods that Apache is providing. This exploit, the executable method that it's using when it actually calls that child init, which is mapped to the Zen destructor, which is mapped to the P destructor, which is mapped to system, all of that actually, the memory location for that is ultimately in libc. So when I reported this to RunSafe, I was like, look, you guys aren't going to love what I have to tell you. I'm already behind in all my deliverables to you, but so I got this working, and now it's not stopping, right? So they're like, oh, okay, let's take a pause. Let's take a look at this. Let's tear this apart. Give us the stuff. Show us what you're working on. Show us how it works. And so, this was something that they looked at it and said, oh, well, here's what we need to do is we need to actually protect the system call in order to stop this exploit. Now, there are probably other ways that that this could be protected against, but that was the choice in this case in terms of the protection to be put in place. And so this exploit was calling the system call by memory location. Now it was able to find the system call, and really this system call, once the interpreted code is inside of the process, the system call is going to be available to it, right? And so when I ran it with not only the protected Apache with liblfr, but I ran it with the libc protected system, you can see some change in terms of the disassemble of the system call. See a couple of things changed, one of which is the name mangling, which is a good visual cue for this. Some other things in terms of the way that the memory actually, the assembly instructions are sequenced there. And so this is where the protection happens, right? For this exploit, the other parts of this, the use after free, the exploit of the Apache out of bound, that doesn't actually stop this, but it's the system call that is actually stopping it. Let's see. That's weird. Let me close this and run this again because that should show this. There we go. All right. So here, the video is showing the system. This is again essentially exactly what I showed in that previous slide. This might be a slightly different instance, and the memory address may be different. But I was running these over and over and over again in order to do the comparisons and the verification and and basically develop an understanding of how it was actually stopping the exploit. So here, same thing. We've got the system. This is the disassembly of that system in terms of the protection that's in place. Effectively the same setup. I've got my little script looking for the presence of seized it. Give me 1 second and I'll find the PHP code again that I ran. I did this video earlier. I had a lot of different components in place for running this. Basically the same environment in terms of the request being made. This then I run the exploit according to PHP was successful. just like in the previous one. I run the exact same set of commands in order to do the graceful restart. In the previous iteration, that seized it was there immediately, and so I was like, okay, well, basically, on the previous system, without the libc protected in place, this actually would run probably 9 out of 10 times and be successful, and one time it might fail, and oftentimes that was just the first time. So here I rerun this a few times to see if I can get the exploitation to work. Basically don't get the exploitation to work, right? And the sort of protection that's in place is that system is available at the memory address that it advertises that it's available. But because the liblfr has modified that ever so slightly for it to still work, but components of it are not in exactly the same place as the exploit expects for them to be in the same place. Now that call to system fails to operate exactly as the memory structure that had been crafted in order to trick the Apache parent process to running. And so, and I'm gonna say my last couple of things on this in terms of the description of the attack and the mitigations, and then I'm actually going to ask Shane to comment on it before I do my final conclusion, just because this is a stopping the exploit, which is exactly what the intention was. But the question would be, well, can the attacker figure out from the position where they are if they could do something different from within the running process in order to be successful in spite of the protections? Now, I didn't go and try to redevelop the exploit, right? I mean, that's another set of things that could be attempted in order to try to modify the existing exploit to go further in order to try to either, right, look at what exactly liblfr did with system and then use that in a way that might accomplish effectively the same thing. And, as Shane mentioned in his intro, the recompilation isn't removing or adding code, it's moving the existing code into its various places that are then managed by the liblfr, which is included in order to get the compiled code to the right place where the LFR mechanism is protecting that code. And that specific location is developed at runtime. But with this use after free, could it basically say, okay, well, I'm going to first detect that this is liblfr protected as opposed to non-liblfr protected. And then I'm going to implement a different technique in order to attack this. I mean, maybe. And I didn't try to go then and develop that, but that's maybe a scenario. And then the other one is, could the PHP script use proc self maps in the same way that it did earlier in order to basically go through and find all the stuff that it thinks that it needs to find? Okay, so those are the two scenarios that I came up with where this product is breaking the exploit, but then a truly motivated attacker tried to go forward. And so Shane, do you want to say anything related to that?
Sure, Chris, thanks. I think there's a few different things to think about. So as we look at exploitation and attacks and defense.
Maybe I caught him off guard.
Can you not hear me?
I'm not hearing you, Shane, if you're talking.
I hear you fine, Shane.
Or maybe he's having a microphone issue with that.
Can everybody hear me now?
Yeah, I can.
Let me do the next slide, and then we're gonna wrap up here in a little bit. So he can comment at that point. So the CARPE DIEM Apache flaw within prefork C and the PHP use after free flaw are not specifically covered by the lib LFR mitigations in place because neither of them actually depend on a randomization of specific memory locations. Okay. What does provide coverage and actually stops the exploit from being successful is the relocation of the system call and the integration of the liblfr protections within the relocated system call that make that system call different enough from what the PHP use after free is attempting to actually structure in order to make it so that that exploit portion then fails. And so again, if the attacker wanted to go forward where they noticed that the exploit didn't work, even though it should work ostensibly on the environment that they're working on, oh no, sorry. Then I'm really sorry. I really didn't hear you. So let me just finish up and then basically talk about it. You can talk about it, and I sincerely apologize for I'm not sure why I'm not hearing you. But so this is basically the mechanism where this would not work. So you want to go ahead, and I'm not sure why my audio is not working where I can't hear you.
Yeah, sure. Thanks, Chris. So there's a few things that we want to think about as we look at exploits and attacks and defense, and part of that is understanding the context. So in this particular case, the PHP use after free attack is able to execute arbitrary PHP code, including reading files from disk. So if you're deploying Apache PHP somewhere and you get you allow the users to upload a PHP file, then execute it. That's generally bad practice. But in this particular case, the exploits work because they were able to find system by reading the ELF symbol table from the libc on disk. And that's where our applying Alkemist source and the LFR transform to libc was able to provide the protection as needed, because then reading the offset on disk and calculating the base address plus the offset now puts system in a different place because we randomized it at runtime. Now, the other side of this is that we still advocate customers to apply the Alkemist source protections to the binaries that are loading libraries in memory, because what we don't want to have happen is a similar thing when ASLR was introduced, where attackers quickly found out that protecting or attacking a program that was protected with LFR was difficult, right? You need an information leak to be able to compute the base address and then to carry out your attack reliably. But they quickly realized software developers are slow to upgrade their shared libraries. And so you saw a whole rash of new attackers and new attack methodologies defeating ASLR by just finding libraries in memory that weren't protected. So we're very thankful to Chris and the SANS team for helping us identify that we needed to change some internals of our code to better protect shared libraries and make them a little bit more resistant to return to libc style attacks. But at the same time, we still advocate that people apply this as broadly as possible to make exploitation of those software packages as difficult as possible.
Okay, that's great, and I sincerely apologize about talking over you. Looks like my amp that has my sound it had shut off, so I didn't hear when you were talking. All right, so we are almost out of time, but Jessica, do you have any questions from the audience? Maybe we have time for one question, or do we not have time?
Yes, we have time for a question. Someone was mentioning about the paper name if you have that, Chris.
I don't recall the exact paper name. The paper has not been released yet. I can't remember exactly what the title was, but you can look for the Run Safe Alkemist paper, and I think that it'll be probably about a week or so for that to actually be finally released. So this is the if you search for preventing runtime exploits, SANS implementation, that it will be in the reading room. And actually, I know that Jessica posted the link earlier about the paper, so that's available in the chat, and we can probably repeat that.
Yes, I had just linked the reading room, and then we have the title for it as well in there. So I'll do one last question for Shane. What operating systems and platforms does Alkemist support?
So Alkemist, with our source and binary transforms combined, we can work on Windows systems, Linux systems. We can do pretty much any RTOS as long as it's using LPE or an S record to be loaded. And we work across ARM, Intel, and PowerPC.
All right, great, thank you. So that's all the time that we do have for today. Any unanswered questions can be sent to q@sans.org. And thank you both to our speakers, Chris and Shane, for that great presentation, and to RunSafe for sponsoring this webcast, which helps bring this content to the SANS community. To our audience, we greatly appreciate you listening in. For a schedule of all upcoming and archived SANS webcasts, including this one, please visit sans.org/webcast. Until next time, take care, and we hope to have you back again for the next SANS webcast.